Hi all. I've been meaning to get back to my 6502 VGA project for a while now. In this video I'm going to talk in particular about increasing the horizontal resolution. I'll talk through some of the timing considerations in detail, both in the old 160 by 100 configuration and what needs to change to get up to 320 by 100, and then show you the results on a breadboard and monitor. I actually recorded this back in December, but didn't find the time to edit it together properly until now, so sorry for the delay, but I hope it's interesting. I do like juggling several projects alongside each other, but I need to get better at keeping all the balls in the air. On that note, if there's anything in particular from a past video that you'd like to see me go back to, please do let me know. So the VGA resolution I'm doing this based on is 640 pixels across by 400 pixels up and down vertically. And in order to get this 160 by 100 resolution, I'm dividing both of those by 4. So every pixel I output horizontally is actually composed of 4 sub-pixels in the underlying resolution. And similarly vertically, every line of pixels I output, I actually output it 4 times to make up the 400 rows that the base video mode requires. And in addition to that visible area, there's also an overscan portion, which includes a horizontal sync pulse. And in all standard 640 VGA resolutions, the horizontal timing is basically the same for those. It goes out to 800 pixels. And at that point we go back and start rendering the next line. Similarly vertically, after the 400 rows are all rendered, there's another 49 rows in this video mode, which includes the vertical sync pulse and the vertical front and back porches. And in order to store all of this in memory, I also have to add some padding. Because I'm using totally independent horizontal and vertical counters, the horizontal number needs to be padded up to the next power of 2, so as far as the memory is concerned, there's another few hundred pixels here going out to 1024. And similarly vertically, the memory comes in power of 2 sizes, so when we get to the end of the frame, there's another few rows here to pad it up to 512. Incidentally, this is why I'm using 400 pixels vertically instead of the 640 by 480 mode. Because in the 640 by 480 mode, the vertical total here is not 449, it's 525, and that's greater than 512, so I would actually need to pad all the way up to 1024 if I was using that video mode, which would require a much larger RAM chips, and I didn't want to bother with that. And when I divide the horizontal and vertical counts by 4, what we end up with is 256 bytes per horizontal row, so I use an 8-bit counter for the horizontal coordinate, and vertically there are 128 lines, so I only need 7 bits for the vertical counter, total of 15 bits, which is enough to address 32K of RAM. So I'm using 32K RAM chips to encode this information. So next let's have a look at the actual pixel grid and how the timings work in this mode. What I've drawn here are, in bold lines, the pixels that I actually output, so I have 160 of these across the page, across the screen, and 100 of these up and down the screen. And inside that I've also highlighted the VGA subpixels from the 640 by 400 mode. So horizontally there are 4 subpixels per actual output pixel, and similarly vertically. In this video mode, and again all of the 640 wide VGA modes, the pixel clock is 25.175 MHz. Let's call that 25 for now, just to keep the math simple. So that means that every horizontal pixel here corresponds to around 40 nanoseconds. And my big pixels correspond to about 160 nanoseconds. We'll come back to those numbers a bit later, maybe because they're relevant in terms of which speeds of memory and other ICs you need in order to do this. So in order for these pixels to appear on the screen, all we need to do is change the red, green and blue inputs to the VGA connector on the bold lines. So as the clock ticks, you can think of us as moving across the screen like this, and every time we hit one of the bold lines, we need to change what color pixel we're outputting, and then we can keep it steady for the next 160 nanoseconds until the next bold line, when we need to change again. So in order to do that and to keep the pixels stable between the bold lines, I use an 8-bit D flip-flop as a kind of latch, and in order to make it actually output the pixels, we need to latch that D flip-flop or clock it on the bold lines. So I've indicated that here with the letter L. In addition, at some point between the points where we latch it, we also need to increment the horizontal count so that next time we latch it, we read a different byte out of memory. So that's indicated here by the letter C. The actual location of that clock is not critical in my design. It turns out to be one of the least important things. Also, for that latch to function correctly, for a certain period of time before and after the latching point, we need the video address to be consistent on the address bus, and we need to give the RAM enough chance to output a sensible data value to the D flip-flop. And so I've indicated here a certain duration of time which I've called vid bus, which is the time in which the video display controller is in charge of the video RAM's bus, both its address and data buses. And during this period, the video RAM is also in output mode. So in fact, the video RAM is what's driving the data bus there. This needs to start a certain amount of time ahead of the latch, and potentially needs to be held for a short duration after the latch. I didn't check the data sheets accurately for this, but it seemed prudent to give a little bit of space on each side. If you do the maths, then there's a few things you need to bear in mind here. The latch itself will have a setup time, so you need to allow for that. And then before that setup time, we need to allow enough time for the data coming out of the video RAM to stabilize on the bus, which depends on things like bus capacitance and things like that. That should be a fairly short time anyway, in comparison to the other times here. Then before that, you have the amount of time it takes the video RAM to look up the address you've provided it with and consistently output data onto the data bus. And then prior to that, you also have the amount of time it takes for the counter chips to set up that address for the video RAM on the bus there as well, because they have a certain amount of delay after I turn on their output enable before the data that they actually put onto that bus is good enough for the video RAM to be able to start looking for that location in memory. And there's one additional element which I haven't put on here yet, which is that we also need the CPU to be able to update the RAM. So we can't just give the video controller the bus the entire time. We need to have these gaps during which the CPU can perform its write cycles. The CPU doesn't need to perform a write cycle on every pixel, but it does need to be able to perform writes from time to time, and so it doesn't really change what we do with the maths here. We basically need to make enough space on every cycle for the CPU to do a write, and then it will write or not depending on what it's actually executing at the time. During this period in the middle, we are going to be giving the video RAM bus to the CPU instead of letting the video controller drive it, and at some point during that time we're also going to be issuing a write to the video RAM. So let's assume that this middle period here is a write cycle for the CPU writing to the video RAM. So this is the video RAM write enable signal, which will just get dipped low somewhere roughly in the middle of this kind of period here. So that's the video RAM write enable signal. In addition, we also need to give the video bus to the CPU, and that's just the inverse of this vid bus signal here. So we kind of want the bus to be on the video side for this period here, and then where I've not drawn a line, we want to give the bus to the CPU, let the CPU's address and data buses drive the video address and data buses. And then prior to this point, we need to give that back to the video controller again. And you can see I've indicated that here for this cycle in particular by marking a period of time where we need to make sure that the CPU is driving this bus. Again, there needs to be a setup time here. We need to make sure that the address that the CPU is putting on the bus is valid as far as the RAM is concerned before we tell the RAM to start writing. If we tell the RAM to start writing too early, then the address that the CPU is putting onto the bus here may not have stabilized properly, and the RAM might write to the wrong location. I've also left a short period afterwards, after the write ceases, before we release that bus, and again that's just to keep the address stable. Make sure that we don't suddenly start pushing a completely different address onto the bus from the video controller, and maybe the RAM would scribble across memory if we do that. So I'm being a little bit conservative here by allowing a bit of space afterwards as well. So next we need to make sure that the CPU is actually ready to perform a write when it gets to this point, which is just a matter of synchronizing the CPU clock to the kind of pixel clock here. And the way we do that is by driving phi2 such that phi2 being high ends at roughly this point in time. So here's the CPU phi2 signal. This ends up being a quarter of the VGA pixel clock, so that's 6.3 megahertz. It's slightly delayed from this latching point. I think I delayed it by half of the 25 megahertz clock just to get it in the place I wanted it. But this signal is actually used in the circuit in a couple of different places. It is the main clock for the CPU. It also controls whether the video RAM is outputting to its data bus. So the video RAM's output enable is directly driven by this line as well, so the video RAM only outputs to the data bus when phi2 is low. That corresponds to this line up here. And the counters as well only write their data onto the video address bus while phi2 is low as well. On the flip side, the inversion of this signal is used to control the bus transceivers which connect the CPU buses to the video address and data bus. And again, they only write their data to the video address and data buses during the high period of phi2, simply by having their output enable signals driven by an inverted phi2. So that's pretty much how my current circuit works, outputting 160 by 100. What would it take to double that horizontal resolution? Let's talk about that one first, because that's the more tricky of the two. Obviously, if we want to double this resolution, we're going to need to latch in the middle of these cycles as well, because fundamentally we're going to want the data going to the VGA port to change at this halfway point. So one obvious thing would be just to latch the latch here as well, and to do another address setup here, double up the counts. You can kind of see that might work for just the video side of things, but it wouldn't really leave any space for the CPU to be writing any data in there. So I don't want to do that. I mean, a side question there is, can we just speed everything up? Can we shorten the amount of time that the video circuit needs to be driving the bus here? Can we shorten the CPU's clock cycle? I've tried that. I've tried a few different variations on that and not really succeeded with anything there. The CPU is quite happy to run at double this frequency. The difficulty is the video RAM itself, I believe, is not fast enough. Or rather, the combination of the video RAM with the latch and the counter, maybe the bus transceivers as well. When you add up all of the times that it takes them to shift states backwards and forwards, it just doesn't fit in when you speed them up. I have tried this in practice as well as in theory, and again, the CPU is quite happy to run at that speed. Everything else works fine, but it can't successfully write data into the video memory. So that's a no-go. Like I said before, I think the only option there to speed that up would maybe to just improve the speeds of all the other components in the system. But that's quite a lot to change. I don't really want to go there. So what are our other options? If you constrain the problem to having the video circuit only access the memory during these same periods that we've already marked here, obviously what it means is that when we do this latching here, we need to latch 2 pixels worth of data from the video memory. And then at this halfway point, we need to swap which of those 2 we're actually displaying. And 2 main ways to do that spring to mind. One very standard way to do this is using a shift register. Typically this is used where you are actually latching enough data for more than 2 pixels. So for example, if we were doing all 4 of these pixels, a shift register would make perfect sense, because we would load the shift register here, and then we would clock the shift register once per pixel as we move across this cell until the next one. And that would make perfect sense. That works really well for monochrome data. It's a bit trickier for color data. For color data, you kind of need 1 shift register per color channel. Or another variant is that you can use a shift register with parallel outputs, and be very careful about how you pack your color data in. It's possible to make that work too. That's how the BBC Micro did it a long time ago. It leads to a very interesting video memory format. One problem with that approach, though, that makes it not really work for me here is that I don't actually have any shift registers which allow me to both parallel load and have parallel output at the same time. I only have parallel in serial out or serial in parallel out. So if I was using shift registers, I would probably need one per colour channel. I think I am going to go down that route, but not for this part of the project. I am in the slightly longer term looking into getting full resolution VGA up and running, and I think that is going to require the multiple shift register approach. For this though, simply for doubling things, it's not necessary. So what I can do here is I can continue to latch with the same D flip-flop I'm using now. I can latch the 8 bits that are coming out of the video memory at this point, and I can use the top bits, as I already do, as control signals for the rest of the circuit. That's not going to change. But the bottom 4 bits, I'm currently using them to define one of 16 colours for the entire pixel block. Instead of that, I'm going to pick 2 of those bits and use those to define one of 4 colours for the first half of the block, and then I'm going to switch to the other 2 bits to define the colour for the second half of the block. And the way I'm going to do that is simply by using a multiplexer. Ben Eater's used these in a number of places in his circuits. I think they're used quite extensively in the 8-bit computer. He uses 4 times 2:1 multiplexers, and these ICs provide 4 bits of output data, and for each bit there is a choice of one of 2 bits of input data which gets passed through, and there is a single signal which gets passed into the IC which tells it whether to take the first or the second channel of data for each of the 4 bits. I only need 2 of those for this because I only have 4 input bits here. I don't have enough space for all 8 input bits. Maybe that's something we'll tackle later. For now I'm just going to use 2 of the channels of one of those chips, and I'm going to wire the selection pin into one of the clock signals, which will be low at the first half of the pixel and high for the second half of the pixel. Low for the first half and high for the second half. And I'm hoping that when I do that, it will all just work and I won't need to make any significant changes to the actual code driving this. Okay, so here we are with the changes made to the circuit. Everything beyond this point is a fairly standard Ben Eater 6502 build as before, so we can ignore all of that. And the rest is mostly the same as the Simple VGA circuit that I've shown here before. We have some control logic here, some bus transceivers to interface the CPU's address and data buses to the video circuit, a crystal oscillator to time everything, a 4-bit counter, and 3 8-bit counters, and the first gives the horizontal count and the other 2 provide the vertical count. Then we have the video RAM hooked up to the counters, and the RAM outputs to the 8-bit D flip-flop over here, and the outputs of the D flip-flop now go through this new multiplexer. The RGB signals then go from the multiplexer to the VGA socket, while the sync signals come straight from the D flip-flop. Finally, over here I've put an inverter. The input signal coming in here is from the clock, and it's meant to drive the multiplexer through the orange wire, choosing which of its inputs get routed to the output. And these chained inverters allow me to add various amounts of delay to this signal by running it through a varying number of the inverters on the way, and so to tune it until I get a good result on the monitor, and I'll show why that was done and what effect it has in a moment. So let's see what this displays on the screen. First of all, I made it draw a kind of test pattern to see various combinations of pixel values. The blue markings at the top correspond from left to writing 1, 2 and 3 into the video memory. 1 is supposed to light up the right hand pixel and 2 the left hand pixel, and as you'd expect 3 should light both at once, and that's all in blue. To the right we then have short diagonal lines drawn in blue and red, and on the left is a longer white diagonal line. And these are the 4 colours I'm supporting at the moment, black, blue, red and white. As you can see, the display isn't quite right. Some of the ones are rendering doubled up, here in the blue test pattern, and again in the blue and red lines, and in the white line as well. Others are rendering too thin, and this is what the inverter is there to fix. The problem is that the phase of the signal that's controlling the multiplexer isn't quite right. It's not properly synchronized with the signal that's latching the data from the RAM, and so sometimes the latch happens offset from the multiplexer, and the multiplexer displays the wrong pixel for a while. So let's move the multiplexer input around on the inverter and see what happens. When it's connected to ground, first of all, it just shows the right pixel for the entire duration, not showing the left pixel at all. And when it's connected to 5 volts, we see just the left one and not the right one. So that's as we expect. Now let's connect it to the clock, and that is pretty badly wrong. It's actually both inverted, so the right and left are happening in the wrong times, and slightly out of phase as well, hence the sort of doubled up artifacts there. So let's invert it once now, and you can see that the lines look better than before, but there are still some artifacts. The phase still isn't quite right. So if we invert it one more time, then once again it's backwards, but it looks like the artifacts are gone now. And I could rewire the multiplexer at this stage to fix the left and right pixels being swapped, but I can also try inverting it one more time, and now it looks pretty good. The phase is pretty close, so we're not getting any artifacts there, we're getting nice clean diagonals. There's still some stretching on some of the pixels, but I think that's actually due to the timing for this video mode not being quite right, rather than the multiplexer. Basically, this 640 by 400 video mode, I'm finding it very difficult to find an LCD panel that actually recognises the sync signals as being 640 by 400. They all recognise it as being 720 by 400, and as such it ends up being kind of stretched because the clock's not properly timed. So I'll address that in another video, but for now I'm happy with this result. Next up I have another test pattern. This one just fills each line of video memory with a constant byte value. The top line is set to zeros, and so it shows up as black. The next line is set to ones, and these show up as the right hand pixel being lit in blue. The third line is twos, which light up the left hand pixel instead, and the fourth line is set to threes, which light both pixels in blue. After that, going on down the screen, the pattern repeats itself, but with the right hand pixel also lit up in red. That's 4 through 7. Then for 8 through 11 it repeats with the left hand pixel red instead, and for 12 through 15 it repeats again with both pixels lit up red. So we end up with both of them being white overall. The shades of blue and red I chose here have a bit of green in them, so it does balance out to a proper white colour when they're combined. Then we have the obligatory Gouldian Finch, of course. I haven't re-encoded the image for this resolution or colour depth, so this is encoded for 160 by 100 with 4-bit colour. So interpreting it in this mode, we see a variety of dithered patterns instead of all 16 colours. It's still nice though to see the combinations of pixels working well with good contrast and no artifacts. Finally, my program fills the screen with stripes and starts writing random values to video memory. I use this as kind of a stress test, and it's caused a lot of timing issues in this circuit in the past. Things like the wrong RAM addresses getting written and things like that show up pretty quickly with this test. And I also leave it running like this for several hours or overnight, and I check it doesn't crash or corrupt the video sync data, which it would do if there were issues with the RAM write timing. So there we have it running well at 320 by 100. It's an odd kind of stepping stone, rather a stretched resolution of course, and the next step is going to be to double up the vertical resolution to match. And in particular that involves providing more RAM and implementing a banking scheme so that the CPU can access it all. I'm going to cover that in another video. It's already recorded, but again needs editing, so hopefully I'll get time to publish that soon. So hopefully I'll see you then.